Alright, so today's video is lesson 3 for chapter 6 on unit 3 field theory, and this is going to be general relativity. So we've talked about gravity a lot. We say gravity is a force. We analyzed Newton's laws, and then we did Newton's law of universal gravitation. Okay, but now we're going to talk about models. So there's a difference between a law and a theory. A lot of people have the impression that a theory is just not a strong scientific fact, right? It's something that's unproven. That's not true. A theory is extremely well proven, and the instant something doesn't prove it to be right, it's no longer a theory anymore. So what's the difference then between a law and a theory? Well, a law involves mathematics. Okay, so if you have a mathematical description of something like Newton's law of universal gravitation, which says this, which we've gone over, that's a law. Let's move this closer. So then what's a theory? Well, a theory tries to explain things with visuals that we can actually see what's going on. So let me give you an example. When Newton came out with this law, this was amazing, right? It unified the motions of the stars and the objects on the Earth, and it accurately predicted everything that they needed it to predict, except for one thing. It didn't predict Mercury. So Mercury, as we learned before, has an eccentricity, which clearly you would be able to tell it's not circular. Okay, so there's Mercury. Well, sorry, let's make that the sun. Let's make this Mercury. Mercury would be like this. And Newton's law would correctly predict that. However, that's not exactly how Mercury orbits. I'm going to exaggerate this a bit, but Mercury orbits like this. Okay, I think you get the idea. But Newton's law of universal gravitation doesn't predict that kind of motion. It just predicts this over and over again, which is not what happens. And then also, a lot of people were upset with Newton's law of motion. They thought that it was almost like going to an occult. How can you have something exert a force on something else without some sort of contact? Right? There's nothing in between the sun and the earth. How can the sun pull on the earth? And I put this quote on your handout, which I quite like. This is something Newton said himself. He said that one body may act upon another at a distance through vacuum without the mediation of anything else by and through their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. So basically everybody who said to him, how can you possibly say this force, this invisible force, acts through a vacuum with no mediation between them? And Newton says, I am not saying that. I have no idea how this works. I just know that it does mathematically show everything correctly. And so people were content, right? So at that time we had a law of gravitation, but we didn't have a theory of gravitation. So we had a mathematical description, but no visual to actually understand things. And so we also had the problem of Mercury, but people were willing to overlook that for hundreds of years until Einstein. So Einstein and Maxwell showed that nothing travels faster than the speed of light. And when Einstein showed this with his special relativity, he was immediately at clash with Newton, because Newton's idea of gravity was that gravity acts instantaneously. So let's look at an example here. Let's go back. We have the sun. Sorry, I don't have great animations or anything. Pictures. Here we have a planet. Let's take the Earth. And the Earth is orbiting around the sun. Now Newton says that if that sun were to disappear, instantly the Earth should follow along a tangent. However, that would mean it must travel faster than light, because it takes light 8.5 minutes to go from the sun to the Earth. Okay, what Einstein's saying is nothing can travel faster than light, so what should happen is if the sun were to disappear, the Earth should continue to orbit for 8.5 minutes and then go off on a tangent. And this was a big thing, right? Coming up with an idea that clashes against Sir Isaac Newton was a big deal. People didn't do that. It was Sir Isaac Newton. Even hundreds of years after his death, people didn't argue with Sir Isaac Newton. So he needed to come up with a way to explain this. It took him 10 years of a lot of hard work and much more difficult mathematics than his special relativity, which is why he had some of his students like Riemann help him with the math. Which is why if you look on your equations on this sheet, you don't need to know these equations. They're far too advanced for you, but I have so many students always asking me, what do the equations look like? So they're there if you're curious, but we will never use them or talk about them or explain them. Okay, but I mean, you could look at it, and eventually if you continue in physics and you see that equation down the road, you might remember, hey, I know what that was for. All right, so let's go back to Einstein. So I put a quote in here from Einstein. He said, I was sitting in a chair at the patent office in Bern when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. I was startled. This simple thought made a deep impression on me. It impelled me toward a theory of gravitation. So what does that mean? What is it actually talking about? Like right now, if you're watching this video, you're probably sitting down and you probably feel a force right between you and the chair, which is strange. What exactly are you feeling? Right? You should be able to feel forces, right? But yet, if you were to remove the chair, you would fall. They would hurt once you hit the ground, but between the chair and the ground, you wouldn't feel anything. And that's what Einstein's saying. If you were to jump off of a ladder, while you're in free fall, you feel nothing. But why do you feel nothing? The force of gravity is acting on you, isn't it? So why do you not feel it? And that's his big question. And that's what led him to this force of gravity. So let's look at an example. Let's say you have a person lifting a weight, okay, on a long bar, and then you have two big heavy weights on either end. Now the bar bends. Why does it bend? Okay, it's standing on the surface of the Earth here. Why does it bend? Well, we could say it bends because the force of gravity acts on both of those large weights. Okay. Could you make it bend just like that without the force of gravity? Take a minute to think about that. If I removed these forces, is there a way for you to still make it bend just like that? If you want to think about it, pause the video. Okay, so let's look at this. Let's take this person, put him inside of a rocket ship. Oh, ground here in the rocket ship, and then have the rocket ship accelerate in that direction. I'm not going to say that's up. That's not up. We're in space, just in that direction. Well, if he accelerates in that direction, this person's holding on to the center of this bar, and the heavy weight's own inertia causes it to bend like that. So if you were accelerating, you would have no need for gravity. In fact, if you were accelerating, those forces would seem to appear because you're accelerating. You're in a non-inertial frame of reference. And so it's almost like gravity is a fictitious force because you're involved in a non-inertial frame of reference. that's all fun to think about, but what does that mean for the Earth? Does that mean the Earth is accelerating that way? Would it? It kind of sounds kind of strange. If it was accelerating in one direction, wouldn't we leave everybody in the southern hemisphere behind? That's obviously not happening. And I could call someone in Australia right now and they're going to say, nope, you're crazy. So we're not leaving everybody behind. Okay, well, what if this was happening? Instead of having the Earth accelerate in one direction, what if you had the Earth expand in all directions? That way, everyone in the north and southern hemisphere would both feel the same force of gravity. How's that? Does it bother anybody? Probably bothers you. Like, the Earth's not getting bigger and bigger and bigger, is it? All right. We're kind of stuck at a crossroads here. So what I'd like you to do is pause the video, and I'm going to attach another video, which in the classroom, in the Google Classroom, and I want you to go watch it right now. It's a quick recap of what we've been talking about, because we've been talking about a lot. This lesson is all theory and no math. So go watch that video. It's by the Perimeter Institute. It's called Alice and Bob. And I can't remember the title of it, but it's about gravity. Okay, so I'm assuming you're back. You watched the video. So let's recap then. We've had a different way of thinking of gravity, replacing gravity with acceleration. But that would mean that the Earth is getting bigger, and that doesn't make sense. So we're going to take a little example. Now in the example, we had Alice jump off a ladder. So let's do this. Here I'm going to draw a distance time graph. Now remember distance time graphs. You can have different graphs. If you have something like this, it means the object is not moving. It's not changing their position. If you have a straight diagonal line, it means they are moving, but they're moving at a constant speed. And if you had a curve, something like this or like this, it means your velocity is changing, so you're accelerating. What we're going to do is we're going to draw a distance time graph, and we're going to compare the motion of Alice and Bob on the Earth. So here we're going to have a ladder. This is at some point, sometime t1. And I'm just going to draw, it's going to be like a visual distance time graph. There's a ladder at some time t1, and this is our space. 3 coordinates of space, x, y, and z. And I'm going to put Alice at the top and Bob at the bottom. Sorry, stick people is the best I can do. Just move this up so you can see. Okay, then at some time, let's make a time later, t3. Here's your ladder, and this is where Alice reaches the ground and is caught by Bob. And then at some time exactly in between t1 and t3, we'll put t2. My ladder got thicker. Just ignore that. I'm just bad at drawing. So at some time exactly in between t1 and t2, Bob is still down at the bottom. But where would you place Alice? Would you place her in the middle because it's exactly in between? Think about it. Okay, you wouldn't place her in the middle because you're accelerating. So during the first half of the time, you've gone from a speed of 0 to something else. So you're actually moving quite slow during this half and much faster during this half. So I wouldn't place her in the middle. I'd place her somewhere above that, like here. All right. Now the question is, who's accelerating? Is there some force of gravity pulling Alice down and accelerating her downwards, or is the Earth actually accelerating up to Alice, and therefore Bob is the one who's accelerating? Well, let's look at whose path through space-time is curved. And to do this, might look pretty obvious, but I'm going to use tape. Because if anybody's tried placing tape on a curved surface, you realize it's pretty hard. It gets kind of crinkled. It's much easier on a flat surface. So let's do Bob. Bob starts here and ends there. I don't see any crinkles in that tape, so it doesn't really look like Bob is accelerating at all. Let's try Alice. Yep, Alice starts here. Kind of a little bit more tricky. My tape's not quite long enough either. Oh, yeah. Alright, so there's lots of crinkles there. All on the bottom part of the tape. Kind of indicates that Alice is accelerating down. So we could say that there's nothing to this idea of Einstein, Newton's right, there's some magical force of gravity pulling everything down. Or have we made a huge assumption when we drew this diagram? What could be the assumption that we make? That's the hardest thing, to remove your common sense, or to even recognize your common sense, which is creating assumptions you shouldn't really make. If you want to think more, pause it. If you're ready to continue, we'll continue. Now here's the assumption we made. We made the assumption that we should draw this graph on a flat surface. Why does space and time need to be flat? That's a huge assumption. Let's draw it on a curved surface. There we go. And I've already done it for us, except it's not as nice as this drawing. Okay, here's our space and time. Here's our first, second, and third ladder, so T1, T2, and T3. Alice and Bob are now circles instead of stick people. I've become even lazier. And again, Bob's always at the bottom. Alice starts at the top, finishes at the bottom, and in the middle, she's not at the halfway point, but slightly above. Okay, let's do this little experiment again. I'm going to put this on for Alice. I'm going to do the same thing for Bob. There's Alice, and now for Bob. Okay, so take a look at that. It's hard on a camera. There we go. So whose path is actually crinkled? Whose path is curved through space-time and whose is straight? In this case, Bob's path is curved through space-time, isn't it? And Alice's is straight. So in this case, if we curve space-time, right, it seems like Alice is the one floating in space and Bob's the one accelerating up to her. And in this case, there's no reason to have to make the Earth accelerate in one direction or to expand outwards, getting bigger and bigger. No, it's just the geometry of the space and time it exists in that is causing that fictitious force of gravity. Okay, well, this is a great theory, but is it right? Well, I'm not going to go over the math because this is grade 12 physics, but the mathematics of this correctly predict the orbit of Mercury. Not only do they correctly predict the orbit of Mercury, they make another prediction. They make a prediction not only of space and this effect of some magical force of gravity, this fictitious force, but they also make a prediction with time as well. Let's look at this event. What's the event? The event is that Alice fell from the top of the ladder to the bottom of the ladder. How much time did that take? Well, from Bob's point of view, it took from here to here. It took that much time. What if we placed a third person on the top of the ladder and from his point of view recorded how much time it took? Well, from his point of view, from here to here. Look at the difference. This much time for our third party, and that much time for Bob. For the same event, they recorded a different amount of time. Well, who's right? Well, they're both right? It's just that time has passed differently for Bob, who is closer to the massive object Earth, and for our third party, who is slightly farther away on top of the ladder. So this predicts that massive objects slow down time. Well, that's amazing, but is it right? And actually, it is, right? GPS only works because we know about this time dilation. And there's been many, many, many experiments to prove that time dilation is true, and that gravity is simply the Earth accelerating up towards you due to the fact that space and time are curved. Okay, so take a moment to think about it. Go through the activities I've posted on the handout. And from now on, when you drop something, I want you to imagine it just stayed where it was. And you and everything else attached to the Earth moved up. Our last lesson for Chapter 6 will be tomorrow on black holes.